All right, and welcome back. Today we're going to be doing the 2024 AB Calc FRQs. These are the most recent, so if you're going to take the test in the next couple of years, I would definitely look at these. But yeah, as always, free Calc 1 book in the description alongside the official scoring guide. But yeah, let's get to it. So for the first one, we're told that the temperature of a coffee cup in Celsius, which is important, is modeled by, or estimated by, this table here, where T is the time in minutes and C of T is the temperature in Celsius. All right. Now, part A is asking us to approximate C prime of 5, which is the derivative at 5, using the average rate of change on the interval from 7 to 3. Okay, let's see what we do. Well, average rate of change, 2-point slope, so it's going to be change in y over change in x. In this case, change in C of t over the change in t. Well, change in t is easy because it's from 7 to 3, so 7 minus 3. And it's the value at 7, which is 69, minus the value at 3, which is 85. All right, and again, you do have a calculator for this first FRQ and the second FRQ. So you're just going to plug this into your calculator, and you're going to get negative 4 degrees Celsius as your value, right? So with this, we can say that C prime of 5 is approximately negative 4 degrees Celsius. And that's it for part A. All right. Now for part B, we're asked to use a left-Riemann sum with the three subintervals that we have from the table to approximate the value of the integral from 0 to 12 of C of t dt. And then we're also asked to interpret what does 1/12 of that integral mean in the context of this problem. Okay? So let's start off with this because it's the more mathy part. Alright, well, Riemann sum, that's going to be the function at some point times the change of x plus the same thing. Alright, we have 3 subintervals and it's a left one. So our first subinterval is from 0 to 3, so it's going to be 3 minus 0 times the leftmost point in this interval is 0, so it's going to be times 100, plus 3 to 7. From part A, we said that this was a change of 4, so it's going to be 4 times leftmost point, so 4 times 85, plus 7 to 12, that's a change of 5, and the leftmost point is 69. So you should get, that's just, 3 minus 0, that's 3, we can all agree on that. So you should get 300 plus 4 times 85 plus 5 times 69. Don't bother doing this by hand. Plug this into a calculator. You should get that the integral from 0 to 12 C of t dt is approximately 985. Okay, that's this part. Now this part. Well, okay. It's the same integral. The key difference is that we have a 12th of that integral. Okay. Well, if you think about it, what is a special kind of integral? Not really special, but one that you should be able to think about. The average value integral, which is 1 over b minus a, the integral from a to b of the function in the differential. Differential is just dx. Okay. Well, if we ignore the 1 over b minus a part, we have an integral. Okay, and then you get 1 over 12 minus 0, which is just 1 over 12, which means that this is the average value integral. Now, what does it mean in terms of the temperature? So because this is the average value integral, that means that the average value of the temperature of the coffee from time equals 0 to 12 is this. So some sentence along the lines of this integral represents the average temperature of the coffee from time equals 0 to 12 should get you full points. All right, now for part C, we're told that C prime of t is modeled by this function from t is greater than 12 but less than 20. greater than or equal to, I believe. And we're just asked to find the temperature at T equals 20, which means we want to find C of 20. Okay? Well, if we have the derivative, we know C of T is the original function. We have its derivative. C of T represents the temperature. We want to find C of 20. To undo a derivative, we have to integrate. Right? So what we're going to do is the integral C prime of T dt. Okay. Well, it's only there from 12 to 20, and we want 20, so we have to put 20 there somewhere. And if we don't have another bound, this just isn't going to work, and we can't do an indefinite integral because we just have a plus c floating around. So, because it starts at 12, ends at 20, we know that at 12, it's 55, so we can do that. And this integral expression is equivalent to c of 20 minus c of 12. Right? So, if this is what we want, we can just do the same integral plus C of 12 is 55. All right. Now, this is the function. You are not going to integrate this by hand. You're going to put this into your calculator. Right? So you're going to put that into your calculator, then add 55. You should get C of 20 equals 40.329. And that'll be it for part C. Very, very easy. Just make sure you slow down and read. All right, now for part D, we're told that C double prime of T, which you can find, but they tell you this, is this function here for the same time interval, which is from 12 to 20. All right. Now we're asked to figure out if the rate at which the change in the coffee's temperature is increasing or decreasing. We're asked to find out if a rate is increasing or decreasing, which means it's the second derivative, which is why we're given it. Okay? So, quick little concept check. If the second derivative is negative, that means the first derivative is decreasing, and if it's positive, the first derivative is increasing. Okay? So, this one, if you look, you can do it two ways. I'm just rewriting this T here. The first one involves very little math, and it is fairly straightforward once you realize it. The second one would be to plug this into your calculator, and then you'll see the graph, and the graph is always going to be positive, which means it'll always be positive, so it'll always be increasing, and that is your answer. The answer is that it is always increasing. However, there's an equally as valid strategy that is a lot faster and simpler. Okay? So, this can either be positive, negative, or 0. Right? In this case, for it to be 0, the only way this is going to be 0 is if t equals 100. Because here we have 100 minus t, so then this will be 0, the top multiplies out to be 0, and this will be 0 over some big number, which is still 0. So we don't have to worry about any zeros. Alright? That's also out of our range, because this is from 12 to 20, we said it had to be t equals 100. 100 is a lot more than 20. Okay? So, no matter what we plug between 12 and 20, at least up here, we're always going to have some positive value, right? Which means this is always positive for our boundary. Same thing here on the bottom. Unless we plug in 0, which we do not want to do because then that's dividing by 0, this on the bottom t squared will always be positive. Okay? And then the last tidbit, this is just some exponential function. The graph of e to the x is always, it's something like that. Not perfectly drawn, but my point is that it is always very close to 0, but then it skyrockets, but it never touches 0, right? So that means this here as well will always be positive. And you might be thinking, hold on, this method that you claim to be quicker is actually might be slower because you have to, like looking at the video length, this might have taken more time to explain. However, Once I saw this function, I automatically knew the answer because I checked, okay, positive, 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 it's always positive. And I just had to write a sentence in my head. Okay? What I'm trying to say with this is, you could go the safe and sound route, plug this into a calculator. It'll take you a second because it's a bit of a nasty function. Look at the graph on your boundary and then go from there. You could do that. There's nothing wrong with that. It's a very safe and sound way, but that takes a bit of time, right? Because you have to plug it in, get the calculator to load, look at it, make sure your window's right, and all that stuff. All right? But I did this in a matter of about 30 seconds in my head. And this is a one-point question. It is meant to be quick. So if you can sometimes think, okay, hold on, can I break this down into pieces to check positive and negative? That is going to save you time and make you a bit better at math, because now you're realizing, when can I break stuff down, how can I manipulate it, and that's good. Mumbling over, if you just go and write a sentence along the lines of, so some sentence along the lines of, since c double prime of t is greater than 0 for the interval 12 to 20, it is increasing at an increasing rate. That'll give you the point. And that's the first FRQ. All right, now for the second FRQ, we're told that there's some particle that has a velocity function modeled by this function here. All right, part A is fairly straightforward. It's just two questions. The first is asking you, when is the particle not moving, aka when is the velocity 0? And the second one is, up to that point, was the particle moving to the right, which is going to be the positive direction, or the left, which would be the negative direction? Okay, well, how you can solve this is, into your calculator, set 0.2t, because this is going to be 0, and we can add this over here, equal to the ln of all of this mumbo jumbo, t squared minus 4t plus 5, right? Plug this into your calculator, figure out where the two graphs intersect. You should get, they use TR to denote when the particle stops, equals 1.426. And this will give you the first half of the question. But now, what you gotta do, that's way too big of a line, is from 0 to TR, we have to figure out if the particle was moving for positive velocity or negative, right? So let's just plug in something straightforward, like 1. So we're going to have ln of 1 minus 4 plus 5 minus 0.2. Okay. 1 minus 4 is 3, plus 3 is 2. ln 2 minus 0.2. Now, I know ln of 2 is greater than 0.2, so I know this is going to be positive, but if not, you just put this into the calculator and you still get positive, right? So with that, we can tell that, from that, you just got to write down something saying that on that interval, which is from 0 is less than t, but t is also less than tr. Tr is the thing we found earlier. The particle moves to the right because the velocity is positive. Something like that will give you the full points. All right, now part B is also fairly straightforward. We're just asked to find the acceleration of the particle at t equals 1.5, and then figuring out if it's accelerating or deaccelerating, right? Okay, so how are velocity and acceleration related? Velocity's derivative is the acceleration, okay? And now you're just gonna find the derivative with respect to time of v of t evaluated at t equals 1.5. This is just saying, you could also just write a of 1.5. You do want to show this because that shows you know how they're connected. Then to actually evaluate, there's a couple ways you can write it. You can write a of 1.5. You could write v prime of 1.5. Those are the two most common. What I was doing was pretty much saying v prime of t at t equals 1.5. Any of these work just fine. You still get the same answer of -1. Okay? Now for the second part, we gotta figure out the velocity to figure out if it's going along the acceleration or against the acceleration. So v of 1.5 is equal to like negative 0.077, something along these lines. You don't care about the value so much as the fact that it's negative. Okay, so that means we have our particle here. We're already going this way. But then as a bit more time passes, we go a little bit further, and so on, which means our speed is increasing. So as long as you show your work, connecting velocity and acceleration, getting the values, that means you know your stuff. Then you just gotta write the sentence saying that since both the acceleration and the velocity at t equals 1.5 are both negative, the particle is speeding up in the negative direction, and that should get you full marks. All right, now for part C, we're told that the position of this particle at t equals 1 is -3. And we're asked to find the position at t equals 4. Okay, how are velocity and position related? The integral from a to b of the velocity function equals the position at b minus the position at a. Okay. And, well, we know that we're going to have it from 1 to 4. So that means we're going to have the position at 4 minus the position at 1. And we know the position at 1 is just -3, right? So we have the integral from 1 to 4 of the velocity function equals the position at 4 plus 3. Let's just isolate the position at 4 to get this expression. This is a 4, not a 9. Let me make sure that's clear. Okay. Now, you're not going to integrate that by hand. Plug it into the calculator. That's all you should do, right? And you should get approximately x of 4 is -2.803. And that's it for part C. And now part D, it's just, you have to make sure you understand one concept and then let the calculator do the rest of the work. We're asked to find the total distance traveled on the interval from 1 to 4. Okay? So what we did in part C, which was just integral from 1 to 4, v of t dt, this gives us the displacement. To find the total distance, it's the absolute value of v of t. Okay? Just, again, plug it in with absolute value bars, let the calculator do the work. You should get about 0.958. And that's it for this question. All right, now for this third FRQ, it is differential equations. The first question is about a slope field. I'm gonna put it up here, and while you look at that, I'll keep reading the question. We're told that this differential equation here models the depth of seawater at some locations, and it's known that at h of 0, it's equal to 4, which is very useful for part C, you'll see. All right, so again, part A, draw your straight line, there you go, goodbye slope field. Easy point. Now, part B is a bit of a mouthful. We're told that for t equals 0 to 5, it's shown that h of t is greater than 1. What does that mean? It's always positive, right? Find the value on the same interval from 0 to 5 where h has a critical point and then determine what kind of critical point it is, and with a justification. Whew. All right. So, this is our equation. We know at critical points the slope equals 0, which means that 0 equals all of that. Well, like the problem said, h of t is greater than 1, so that means that this is always positive. Okay, why does that matter? Because we need to get 0. And this is all being multiplied, so how can we get 0? Well, we can't do anything to the half, that's just a constant. H is always greater than 1, so it can't be 0 here. It'll always be positive. Which means we need to manipulate the cosine of t over 2 to get 0. Well, let's just think about regular cosine. That's a good place to start. Where does cosine equal 0 on the unit circle? All right, give it a second. Well, if you have a unit circle, right, cosine's going to start off here at 1 and decrease until it gets to about here. And it's going to become negative, go all the way to -1, stay negative, and go back to 0 here. Right, so these two big dots is where cosine equals 0. Yes, I know the circle's off-centered. I'm an artist at heart, okay? So we have at t, this is for regular cosine. This is for regular cosine. If theta equals pi over 2 comma 3 pi over 2. Let me make sure I used it. All right, but we have cosine of t over 2. Okay, so that means we want t over 2 to equal pi over 2, and the scenario where t over 2 equals 3 pi over 2. Well, if you see it right away, congratulations. Multiply by 2 on both sides, you get t equals pi. Multiply by 2 on both sides, you get t equals 3 pi. Okay, but which one of these are we actually going to use? Well, our interval is from 0 to 5. 3 pi is greater than 5, which means it's at t equals pi. Right? That's very good to know, because that's a point right there. All right? So now we know when it happens. We got to figure out now what kind it is. So we know where the critical point is. We're going to plug it into the derivative to figure out if it's a maximum or a minimum. All right? If we plug in something less than pi, let's just say pi over 2, into this we're going to get pi over 4, which is going to be over here where these red dots are, and that's going to be positive. All right? If we plug in something larger than pi but less than 5, well, what that means is that we're going to tip over from this green dot into quadrant 2. And cosine is negative in quadrant 2, so this will be negative, which means our function goes near. So this will be a maximum. So a sentence saying that pretty much because prior to t equals pi but after t equals 0, the derivative is positive, and that after t equals pi but before t equals 5, the derivative is negative, h of pi is a maximum. That should give you full marks. All right, now for part C, we're just asked to solve this differential equation using separation of variables, and the initial condition, h of 0 equals 4. Okay. Well, separation of variables, multiply by dt, divide by h minus 1 to get dh over h minus 1 equals half cosine of t over 2 dt. And now we're going to integrate both sides. This becomes the negative natural log, the absolute value of h minus 1. How? Okay. Let u equal h minus 1. du equals negative dh, or positive dh. Right? So then you get the integral of 1 over u du equals the ln absolute value of u. So this is actually positive. That's a good thing I caught it. Which is why you don't want to get cocky and try and do your math in your head. Because I know how to integrate this, but I was thinking ahead and thinking wrong, and one sign error would have cost me a lot of points. Okay, that's the easy part. Cosine of t over 2, that's also u sub. We're going to let u equal t over 2, du equals half of dt, right? So 2 du equals 1 dt. So we get the integral of half, because the half still stayed there, cosine of u, 2 du is dt, 2 du. Well, we're multiplying by a half, then 2. Those are going to cancel out. That's lovely. So we just have the integral of cosine of u. What's the integral of cosine? Sine. So we get sine of u. U is 1/2 t. or t over 2, whatever you prefer, plus c. All right, it's a wonky c. Okay. Now what? Well, now we have to find our constant of integration. Okay. Well, we know at t equals 0, h equals 4. So we get ln absolute value 4 minus 1 equals the sine of 0 plus c. This is ln of 3. We can take away the absolute values because 3 is a constant now. Equals c. Okay. Now for the last tidbit, we have to find h of t, which means we gotta undo all this natural log stuff. Okay. So let me just rewrite the equation with the constant as the actual value that we have now just found. Now how do you undo a natural log? You raise everything to e, right? So we'll have h minus 1 equals e to the sine of t over 2 plus ln of 3, and then we just add 1, and there you go. That's your answer. You can simplify it with all this stuff here, but why would you? You'll get the same point. And that's FRQ 3. All right, for this fourth FRQ, we're given the graph of f, which I'm going to plop up here. Note the shaded region R. I'll come back to that in a second. Right? It's from -6 to 7, has a horizontal tangent at x equals -2, and that the shaded region R, the gray region, has an area of 12. That means the integral from -6 to 0 of f of x dx is 12. All right, let's get to it. Part A, the function g, all right, that's something new, g of x, is the integral from 0 to x, f of t dt. Okay, what do we want to find? We want g of -6, g of 4, and g of 6. Okay, let's start off with g of -6. Right? So that means we want the integral from 0 to -6 f of x, or f of t, whatever, dx. Okay, well, last I checked, we shouldn't start with 0 and then go lower, which means we're going to use the property of an integral where if you flip the bounds and add a negative sign, it's the same. All right? This integral is almost the same as this integral, except this one's negative, which means g of -6 is equal to -12. Awesome. Now, again, I'm going to pop this up. If we have g of 4, we're going to have the integral from 0 to 4. Well, from 0 to 4, that's a triangle. That's good. Triangles are easy to calculate. It's just half the base times the height. This one has a height of 2 and a base of 4. So you get a half times 2 times 4 equals 4. But you do gotta show some fancy calculus to pretend that you need the calculus for this particular part, right? So you just write that the integral from 0 to 4 f of x dx equals 4, and this g of 4. Awesome. Now, from 0 to 6, which is the next part, it's the same triangle from earlier, except now we have a smaller triangle in the negative. That smaller triangle has length 2, base 1, right? So it's going to be a half times 1 times 2 times -1. Why -1? It's underneath the x-axis, so we get -1/2 times 2. That's just going to cancel out. It'll be times 1 essentially. Times 1, still 1. Times -1, that's -1. Right? So that's for the very small little triangle. But we want both triangles, so it's going to equal 4 minus 1, which is 3. And again, write out this integral expression to show that you know what you're doing in terms of calculus. But yeah, part A, very straightforward, although it looks tricky. All right, now for part B, using g of x again, we're asked to find where it has a critical point. Not what kind of critical point, what's the value of it, just where. All right, so graph, movie magic, you know the deal by now, right? Okay, well, if we're looking for where it's a critical point, we want the derivative to be 0, which means we want a slope of 0. But g isn't a function, it's an integral of a function. So let's differentiate it, right? We get g prime of x equals, well, we're going to do a derivative, then we're going to integrate. That's like multiplying by 2, then dividing by 2. So it really just means that we're going to have g prime of x equals f of x. And so we're looking for where f of x equals 0. That only happens on one point in the graph, which, as I'm showing you, is at x equals 4. Right? And they do ask you to give a reason. Write this down on your page somewhere. That'll definitely help you. And then write a sentence along the lines of, since g prime of x equals f of x and f of x equals 0 at x equals 4, g of 4 is a critical point. Something along those lines, you should get full marks. Now for this last part, we're told that h of x equals the integral from -6 to x of f prime of t dt. And we're just asked to find h of 6, its derivative there, and its second derivative there. Let's go with h of 6. So it's going to be the integral from -6 to 6 of f prime of t dt. Which really means, because it's a derivative and then we're integrating, it's going to be f of 6 minus f of -6. Okay? Now, movie magic, I'll show you again because they do highlight this, but f of 6 is -1, and f of -6 is -1/2, which means it's going to equal -3/2. And that's the first point that we want. Okay, let's go for h prime of 6 then. All right, so we're going to differentiate this expression to get h prime of x equals, we're going to differentiate an integral, which means the inside is just going to stay the same. So h prime of x equals f prime of x. Okay. Now we just got to plug in at 6. Well, we don't have a function for f. We just have its graph. But it's a linear function. F is a linear function at and around t equals 6, or x equals 6, sorry. So we can just do 2-point slope, right? So I'm going to take the y-intercept, which is 0, 2, and the x-intercept, which is 4, 0, 2 points that are both on the graph, right? And we're going to go from 0, 2 to 4, 0, which means it's going to be 0 minus 2 over 4 minus 0, which is going to equal -1/2. And there you go. That's h prime of 6. Now for h double prime of 6, we're asked to find the slope of that line. But because it's a linear line, if we take the slope twice, that's pretty much saying take the slope of a constant. Slope of a constant? 0. And that's it. That is it for the 4th FRQ. Now this 5th FRQ admittedly looks deceivingly simple because there's no graphs, it's just equations, and we're giving an implicit function, its derivative. You might be thinking, it's not that bad, and you'd be correct. However, if you are not comfortable with implicit differentiation or with slowing down and asking what do I want to answer, what is asking me to answer, it can be discouraging. However, it's very simple once you see it because it's just asking you to use its derivative every now and then and just rationale. So let's get to it. Part A, at some point on the curve near the point 2, 4, there's another point with x coordinate of 3. We don't know what the y coordinate is, but we want to approximate it using the tangent line. Okay, well, tangent lines, approximations, sounds like we're going to need point slope form, which is y minus y naught equals the slope times x minus x naught. Okay, well, we're going to use this point, so this becomes -4 minus 2. Okay, and we know that this is at x equals 3, so this just becomes 1. Okay, that's good to know. So the y value is going to be approximately equal to the slope plus 4. Okay, we did a lot of work simplifying that, which is good, but now I got to find the slope. So what we're going to do is we're going to take the derivative and evaluate it with this, right? 2 comma 4, okay. Well, let's just plug in x's first. We only see one x, which is lovely. This will make it a lot easier. So we're gonna have negative 2 times 2, negative 4 over 3 plus 4 times 4. That's gonna be 3 plus 16, that's gonna be 19. So the slope at the point 2 comma 4 is equal to 4 over 19. So y is approximately equal to negative 4 over 19 plus 4. Now, you can simplify this, obviously, because it's fractions. Do you want to? No. Do you have to? No. Just leave it as that. All right? All right. Now for part B, we're asked if the horizontal line y equals 1 is tangent to the curve. All right? So we're looking for y equals 1. Okay. Well, if y equals 1 and we want it to be horizontal, that means it's going to have a slope of 0, which means the slope here has to be 0. So 0 has to equal negative 2x over, well, we know y has to equal 1, 7. Okay, so that means x has to equal 0 for this statement to be true. So if 0 comma 1, if this point is on our equation, then yes, the line y equals 1 is tangent. If it's not on the equation, it's not tangent at all, because it's not there. Okay, let's just plug it in. We get 0 squared plus 3 times 1 plus 1 squared equals 48. 3 times 1 is 1. 1 squared is 1. So you get 4 equals 48. I don't know about you. However, that doesn't sound right to me. So I don't think 4 equals 48. So no. Actually, something I wanted to point out real quick. I copied down the equation wrong. It's x squared plus 3y plus 2y squared equals 48. Right? So I did copy it down wrong. I caught it. But actually, my work for part A is still just fine. And although they got 5 doesn't equal 48, 4 also doesn't equal 48. So yes, it's a good thing that I caught it. However, even if you mess up a little bit, sometimes you can still get it right. Do I recommend you mess up? No, no one wants to mess up. But it just goes to show, sometimes if you catch a mistake, you're still fine with all the work you've done. So don't be afraid to look back on what you did if you think, something doesn't seem right. And I only saw it because I was just double checking with the scoring sheet, which is why you always want to check that too when possible. Now for part C, we're asked if the x-intercept of root 48 comma 0 has a vertical tangent line. Okay, tangent lines, we're going to look at the derivative. So vertical tangent line means that the bottom of the derivative equals 0. So let's just plug it in and see what we get. Right, we're going to get dy dx equals negative 2 root 48 over 3 plus 4 times 0, which is negative 2/3 of root 48. So the bottom's not 0, the derivative exists, which means that the x-intercept of root 48 comma 0, the tangent line is not vertical. All right, now for part D, we're pretty much told some particle is moving along this curve, and that at this point, which is 4 comma 2, the change in y with respect to time is negative 2. And we want to find the change in x with respect to time, which means you gotta differentiate and it's gotta be implicit. All right, we're gonna do this with respect to time, so it's gonna be 3y squared dy dt. And then this is gonna be a product rule, so it's gonna be plus left derivative of the right, so 2x dy dt, plus right derivative of the left, so it's going to be 2y dx dt equals 0 because the derivative of 24 is 0. All right, now just plug and chug. We get 3 times 2 squared times negative 2 plus 2 times 4 times negative 2 plus 2 times 2 times dx dt equals 0. That's a lot of 2's in multiplication, so let's knock it out. 2 squared is 4, times 3 is 12, times negative 2 is negative 24. 2 times 4 is 8, times negative 2 is going to be negative 16. Plus 2 times 2 is 4, dx dt still equals 0. Negative 24 minus 16 is negative 40, right? So now we just divide by 4 to get negative 10 plus dx dt equals 0, which means dx dt is 10. And that is it for this 5th FRQ. Now for this final FRQ, movie magic, I'll let you guys look at it while I talk about it. We were given two functions, f and g, there's their equations. All right, part A is fairly straightforward. We're just asked to find, but do not evaluate, an integral expression to give the value of the area of R. Okay, well, we know it's gonna be an integral, and we're looking for area, so it's gonna be with, some bounds, in this case from 0 to 2. And it's gonna be a dx, because we need those in integrals. All right, now, f of x is on top of g of x, so we're gonna have the integral of that minus the integral of g of x. And that's all we need, right? So if you just have the integral from 0 to 2, f of x minus g of x dx, that right there, full marks for part A. Now for part B, the other region, which again, you're seeing here, is S, and it's from x equals 2 to 5, and assuming that S is the base of a solid for which the cross sections are rectangles with the base equal to half the height, we want to find the volume and show our work. That's a lot to say, and a lot more to do, so let's get to it. Well, we know we're going to need an integral. It's from 2 to 5. And we said, well, it's a rectangle, right? And the base, or sorry, the height is half the base, right? Which means that the whole thing is half the base squared. Okay. As for the volume though, we gotta get the area. What's the area? G of x. Sorry, the base, not the area. So it's gonna be 1/2 g of x squared dx. All right. So I'm gonna pull the 1/2 out of here just to leave it for the end. All right, g of x squared. We gotta do the math. That's a minus sign. So yeah, just multiply it out. You should get x to the 4th minus 4x cubed minus 4x squared. All right, so we have half integral from 2 to 5 of that, which is right there. You should be able to see it right now. All right, let's do it. Whew. All right, integrate this. This is all just power rule, thankfully. We get a 5th x to the 1/2 times a 5th of x to the 5th minus x to the 4th minus 4/3 of x cubed, evaluated at 2 then 5. Okay, well we can't just leave it like this, unfortunately. What we can do is the following. We can just plug this all in and leave it as one big expression. Will your grader like you? No. Could you simplify a bit? Absolutely. Would you technically still be correct? Yes. So if you write down 1/2 of 5 to the 5th over 5 minus 5 to the 4th minus 4/3 of 5 to the 3rd, that quantity minus, let me move this out the way, minus the new quantity of 2 to the 5th over 5 minus 2 to the 4th minus 4/3 of 2 cubed. This, you can technically leave it and be correct. Now, do you want to leave it there and make your grader not so happy? Not really. So let's simplify a bit. We're going to keep the 1/2. 5 to the 5th over 5 is the same thing as 5 to the 5th over 5 over 1. Exponent properties, we're going to have 5 to the 5th becomes 5 to the 4th, right? Then you're going to minus that quantity, so it's actually just over here. It's actually just going to be negative 4/3 of 5 to the 3rd minus 2 to the 5th, 2, 4, 8, 16, 32 minus 2 to the 4th, 2, 4, 8, 16 minus 4 times 2 to the 3rd, 2, 4, 8. 8 times 4 is 32. Now this is where I personally would stop it, because anything after that is going to get sloppy. However, if you want to know and you want to keep simplifying, it'll come out to 414/5, and that's going to be it for part B. All right, now for part C, we're asked to write but not evaluate an integral expression giving the volume of the solid generated when the region S is rotated about the line y equals 20. Okay, well, we have volume. We know it's going to be an integral. S was bounded by 2 to 5. And because this is volume, we're going to go around a full circle, which means we're going to have to multiply by pi. Okay, and now there's a quick little sketch. Well, it's something like very rough sketch, a very rough sketch. But we're essentially looking for this area over here, more or less, around this line, right? Well, that means we're gonna have to do big R squared minus little r squared. Okay. So, that means we want the whole thing, which is gonna be 20 squared, because it's about the line y equals 20, right? Minus 20 minus g of x squared dx. Okay, well, why is it 20 minus g of x? Okay, that's because 20 minus g of x is this. Right? These vertical lines is 20 minus g of x. We only want these slanted lines here, which means we're going to have the whole thing, and then we're going to chop off most of it, which is why it's going to be 20 minus g of x, whole thing squared. All right? And that'll be it for these FRQs. Thank you for watching. If you found it helpful, consider leaving a like. If it was really helpful, subscribe. And otherwise, have a good day.